Good evening and welcome to our next course about generalized power series and Frobenius method. Before we get into generalized power series, let us look at one more example of an equation that can be solved by using power series. This is for comparison because the equations we will solve by generalized power series will look somewhat similar to this. So let's consider an ordinary differential equation this time, y double prime minus 2xy prime plus y is equal to x squared. With the initial conditions, y of 0 is equal to 1 and y prime of 0 is equal to minus 1. So note that this is a second order equation. We are using two initial conditions, y of 0 and y prime of 0, and it is linear. So in order to solve this equation by power series, first we should check that the theorem applies so that everything in the equation is analytic. And indeed note that 2x, y prime, y squared are analytic functions of x, y prime, and y. So this equation can be solved by power series, and then we assume that the solution is given by a power series, namely y of x is equal to c0 plus c1x plus c2x squared plus c3x cubed plus etc. So in general, it's sum of cn x to the n for n going from 0 to infinity. This equation contains four terms: y double prime minus 2xy prime, y, and x squared. The first three terms are on the left-hand side, and x squared is on the right-hand side. In order to solve this equation by power series, we should express all the terms in the equation by power series. So let's start with the power series of y. If we know the power series of y, then by differentiating, we can get the power series of y prime, and then differentiating again, the power series of y double prime. So we start with y equal c0 plus c1x plus c2x squared plus c3x cubed, etc. And then when we differentiate each term, the derivative of c0 is 0, the derivative of c1x is c1, the derivative of c2x squared is 2c2x, the derivative of c3x cubed is 3c3x squared, then the derivative of c4x to the 4 is 4c4x cubed, and if we continue, the next term should be 5c5x to the 4th, and then in general it should be n cn x to the n minus 1. Right, so now we again take the derivative of y prime and we get y double prime. So the derivative of power series, again to remind you, can be obtained by taking the derivative of each term in the power series, and then it has the same radius of convergence as the original power series. So within this radius of convergence, the derivative of c1 is 0, the derivative of 2c2x is 2c2, the derivative of 3c3x squared is 2 times 3 c3x, so 6c3x. The derivative of 4c4x cubed is 3 times 4c4x squared, so that's 12c4x squared. And then the next term would be 5c5x to the 4th, and the derivative of that will be 4 times 5 C5 x cubed, etc. So y double prime is given by the sum of this power series. So now we have computed the power series of y double prime. Next, let's compute the power series of minus 2xy prime. Well, we take the power series of y prime and we multiply every term by minus 2x. So minus 2xy prime is equal to minus 2c1x minus 4c2x squared minus 6c3x cubed minus 8c4x to the 4, etc. So notice that now the starting power is x, and every coefficient was multiplied by minus 2. So every power increased by 1 because we multiplied by x, and all the coefficients got multiplied by minus 2. And finally, on the right-hand side of the equation, x squared is already a power series with just one term, namely x squared. So x squared is a power series in itself with just one term. And now we know the power series of all the terms in the equation. We computed the power series of y double prime. We computed the power series of minus 2xy prime. The power series of y is what we started with, and x squared is its own power series. So on this page I have written them again. The power series of y double prime minus 2xy prime, y, and x squared. Now the left-hand side is the sum of the first three terms, namely y double prime minus 2xy prime and y. And the right-hand side is just x squared. So let's compute the power series of the left-hand side of the equation. Well, we have to sum the power series of y double prime minus 2xy prime and y. So in order to sum these power series, we sum them according to the power of x, so according to the degree of each term. First we sum terms of degree 0, then we sum terms of degree 1, then of degree 2, etc. So there are only two terms of degree 0, namely 2c2 and c0. Notice that the other power series does not contain any term of degree 0. So the first term in the power series of the left-hand side is 2c2 plus c0. Then we look at all the terms of degree 1, and now there are three of them. There is 63x, there is minus 2c1x, and there is plus c1x. So overall, in this left-hand side of the equation, the degree 1 term would be 63 minus 2c1 plus c1 times x. So the coefficient of x is 63 minus 2c1 plus c1. And for all the other terms in the same way, we will have three contributions. So the next one is 12c4, so coming from here, and then minus 4c2 and plus c2 times x squared. So these are all the terms that contain x squared on the left-hand side. Then the next one is 20c5 So that's 4 times 5, C5, minus 6, C3, plus C3. So coming from here. So minus 63 comes from minus 2xy prime, and C3 comes from y. So this is how we should add power series, by grouping all the terms of the same degree together. So first we wrote all the terms that did not contain x, then we wrote the terms that contained x to the power 1, then we wrote the terms that contained x squared, then we wrote the terms that contained x cubed, etc. And then on the right-hand side, we just have x squared. So there is only one term, and it corresponds to the power 2, to term of degree 2, x squared, and that's it. All right, so I have written this again on this page. We have the power series for the left-hand side of the equation is equal to the power series for the right-hand side of the equation. In order for these two power series to be equal, all the coefficients of the power series on the left-hand side must be equal to the corresponding coefficients of the power series on the right-hand side. So let's go by degree, so by the power of x. First, let's look at those terms that do not contain x. In other words, the constant terms. On the left-hand side, we have 2c2 plus c0. On the right-hand side, we do not have a constant term. So 2c2 plus c0 is equal to 0. And again, notice that for this constant term, minus 2xy prime had no contribution, because the power series of minus 2xy prime started from the power 1, so from x. Next, let's look at x to the power 1, which is x. So in our power series, the coefficient of x is 63 minus 2c1 plus c1 on the left-hand side. And on the right-hand side, again, notice there is no term just that contains x to the power 1. So we should have 63 minus 2c1 plus c1 is equal to 0. Then let's look at the power x squared. So we get, on the left-hand side, we have 12c4 minus 4c2 plus c2. This is the coefficient of x squared. And on the right-hand side, this is the only time when we have a non-zero coefficient. So the coefficient of x squared on the right-hand side is 1, because the right-hand side is equal to x squared. So we get 12c4 minus 4c2 plus c2 is equal to 1. So this is the only time when the x squared on the right-hand side contributes. And for all the powers, starting from here, so for x cubed, x to the fourth, etc., we'll always have 0 on the right-hand side, because we only had one power of x on the right-hand side, namely x squared. So now we'll have, for example, for x cubed, the coefficient of x cubed on the left-hand side is 20c5 minus 63 plus c3. So that's equal to 0. And so on and so forth, the same for all higher powers of x. Next, in order to compute the power series, we need a starting point, and in our case, we need to know both C0 and C1 in order to compute the other coefficients. So in order to get C0 and C1, we're going to use our initial conditions. So we know that y of 0 is equal to 1. And we start from the formula of y, which is given by this power series. So y of x is equal to C0 plus C1x plus C2x squared, etc. And when setting x equals 0, in order to get y of 0, we're just left with C0 because all the other powers contain x, and when x is 0, this means that all the other powers go away. So since y of 0 is 1, we get that C0 is 1. And in the same manner, we try to take advantage of the condition y prime of 0 is minus 1. So we start from the formula for y prime, which we computed on a previous page. So y prime is C1 plus 2C2x plus 3C3x squared, etc. And setting x equal to 0, we get that y prime of 0 is equal to C1 because all the other higher powers go away. So we get that from the initial condition, since y prime of 0 is minus 1, we get that C1 is minus 1. All right, so now now knowing the first two coefficients, C0 and C1, it turns out we can compute all the other coefficients one by one using the equations we had on a previous page. So it turns out that all the other coefficients depend on C0 and C1. All right, so the first equation we had was 2C2 plus C0 is equal to 0. So here it is, 2C2 plus C0 is equal to 0. Therefore, C2 is minus 1/2 C0. And since C0 was 1, we get C2 is minus 1/2. Then the second equation was 63 minus 2C1 plus C1 is equal to 0. So this means C3 is equal to C1 over 6. And C1 was minus 1, so we get that C3 is minus 1/6. Third equation, 12C4 minus 4C2 plus C2 is equal to 1. So here it is, 12C4 minus 4C2 plus C2 is equal to 1. This means C4 is 3C2 plus 1 over 12. And we already computed C2 as a function of C0. So it turns out that indirectly C4 is a function of C0. And C2 was minus 1/2. So now we get that C4 is minus 1 over 24. Next equation, so from this point on, all the equations that we get will have 0 on the right-hand side because x squared was the only power on the right-hand side that was present. So for all the other powers, the coefficients will be 0. So now, next equation was 20C5 minus 6C3 plus C3 is equal to 0, which means that C5 is equal to 5C3 over 20, so that's C3 over 4, and that's minus 1 over 24 again. But notice that this is probably just a coincidence that both C4 and C5 are minus 1 over 24 because we got them in different ways. Well, so in order to see whether there is a pattern to the coefficients, we probably should compute more of that. In any case, the solution is given by this power series that we have started to compute. 1 minus x minus 1/2 x squared minus 1 over 6 x cubed minus 1 over 24 x to the fourth minus 1 over 24 x to the fifth, and so on and so forth. We don't know yet at this point whether this is a known function, and on the other hand, I can tell you that the general pattern of the coefficients can be computed. It is a known pattern. It is not one of the elementary functions that we mentioned in a previous course, so it's not going to be e to the x or sine x or cosine x. It's a less well-known function. Y of x is given by some sort of generalized hypergeometric series. And this is none of our concern. This is somewhat hard to identify given what we are doing in this course. So for us, all we can do here is compute as many coefficients as we want. Okay, so in general, this method that I have described so far of expanding a solution into power series works when we are dealing with an initial value problem, which is written here in a general way. The nth derivative of y is some function of x, y, and all its derivatives up to derivative n minus 1, when f, this expression involving all the derivatives except the highest order derivative, is analytic near the starting point. So it's an analytic function at the point of coordinates x0, y0, y1, up to yn minus 1. So, for example, let's consider a complicated equation. Y triple prime is equal to y double prime plus sine of y prime times y squared, everything divided by x squared. I don't know anything in particular about this equation. I just want to find out whether it can be solved by using power series or not. So at our starting point, we're asking what about the initial condition? Y of 1 is equal to 0, y prime of 1 is minus 1, and y double prime of 1 is 2. So our starting point has coordinates x0 is 1, and then y0 is 0, y1 is minus 1, and y2 is 2. And we notice that at the starting point, the function is analytic. So everything can actually be expanded into a power series that involves y double prime, y prime, y, and x. So we could solve this equation by the method of power series. On the other hand, the same equation, if we try to solve it at another point, may not be solvable by power series. So this is a point where it's not solvable by power series. Corresponding to the initial conditions, y of 0 is 0, y prime of 0 is minus 1, and y double prime of 0 is 2. So the reason is that we are trying to solve it at the starting point with x coordinate 0. So we're trying to solve it around the point x0 is equal to 0. Well, the right-hand side of the equation contains this fraction with x squared on the denominator, and therefore it's not a continuous function at the point where x is equal to 0. And analytic functions are continuous, so this fraction, this pretty complicated expression, is not analytic at our starting point. Therefore, we cannot solve this equation by power series for this initial condition. In fact, it turns out that this equation can be solved by power series at any starting point for which we are not taking x to be 0. So any initial condition stated at any point for which we do not start with x being 0. Points at which the equation is solvable by expanding everything into power series are called ordinary points. So if we can solve the equation by power series starting at some point, or by expanding into a power series around a point, then that point is called an ordinary point. The exceptional points where the power series method fails are called singular points. So in our example, all starting points are ordinary points except for 0, which is a singular point. However, there exists a subclass of singular points which are called regular singular points, at which we can solve an equation by a more general version of the power series method. Instead of using power series, we'll use something called generalized power series. This is called the Frobenius method. We are going to use the Frobenius method only to solve linear equations, and to make it simpler for us, we'll only try to solve second order linear equations. So let's consider a second order linear equation written in this form: y double prime plus p of x y prime plus q of x is equal to 0. Then the point x0 is called a regular singular point for this equation if it is not an ordinary point. So P and Q are not both analytic around the point x0, but x minus x0 times P and x minus x0 squared times Q are analytic at around the point x0. So let's consider an example. Y double prime plus 2 over x minus 1 y prime plus cosine of x over x minus 1 squared y is equal to 0. So I tried to make it a more complicated equation. And here, all the points except 1 are ordinary points because we can expand these functions 2 over x minus 1 and cosine x over x minus 1 squared into a power series around any point other than 1. We cannot do it at 1 because these functions are not continuous at 1, because we are dividing by x minus 1. So these functions are not even defined at x equal 1. So this means that x equal 1 is a singular point. However, let's check whether it is a regular singular point. So the coefficient of y prime is 2 over x minus 1. So this is p of x is 2 over x minus 1. And q of x, coefficient of y, is cosine x over x minus 1 squared. And then by the definition of a regular singular point, we have to check whether x minus 1 p of x is an analytic function, and x minus 1 squared q of x is an analytic function. And x minus 1 p of x is just 2, and x minus 1 squared q of x is cosine of x. Both 2 and cosine of x are analytic functions, including at 1. So this means that 1 is a regular singular point. So here is an example of a singular point which will not be regular. Let's consider the equation x cubed y double prime plus y is equal to 0. First, we need to bring the equation to the standard form y double prime plus y over x cubed is equal to 0. So in this equation, the coefficient of y prime, p of x, is 0 because there is no y prime in the equation. And the coefficient of y is q of x, which is 1 over x cubed, because we have 1 over x cubed times y in the equation. So both 0 and 1 over x cubed are analytic functions at any point other than at 0. And 1 over x cubed is not an analytic function at 0 because it is not even continuous at 0. It is not even defined at 0. So 1 over 0 is not defined. And then this means that 0 is a singular point because q is not an analytic function at 0. However, let's now check whether it is a regular singular point. So x times p of x is x times 0, which is 0, which is an analytic function. On the other hand, x squared times q of x is x squared times 1 over x cubed, which is 1 over x. And 1 over x is still not an analytic function at 0, again, because it's not continuous at 0, it's not even defined at 0. And then this means that 0 is not a regular singular point. So this means that the method of Frobenius, the method of generalized power series, will not work for this equation. So presumably this equation is harder to solve than other equations that we'll be looking at today and in the next course. All these equations that I am talking about and which I am showing you actually have many ordinary points. Almost all points are ordinary points, and they can be solved by power series at ordinary points. For example, for this equation, x cubed y double prime plus y equals 0, we have no special difficulty in solving it if we solve it for an initial condition starting not at 0. So, for example, y of 1 is 3 and y prime of 1 is minus 3. So we can solve it in that case by using power series. However, we do have a special difficulty at 0, which is the singular point. It turns out that solving the equation at the singular points is, in general, more interesting and more important than solving the equation at the ordinary points. It will tell us more about how the solution looks like. So even though there are many fewer singular points, if we can solve the equation at a singular point, then we should try to do it because they are more important. And this solution method also works for higher order linear equations. So Frobenius' method also works for equations of degree of order 3, 4, and higher. But it's just slightly more complicated, so no need to get into the details in this course. And it is important that the equation should be linear, otherwise everything becomes much more complicated. So now that we know what a regular singular point is, how does one solve the equation at a regular singular point? Instead of using a power series, one has to use a generalized power series. This means instead of starting with x minus x0 to the power 0, x minus x0 to the power 1, x minus x0 squared, x minus x0 cubed, we start with some other power. So maybe the first power is x minus x0 to the alpha, next power is x minus x0 to the alpha plus 1, x minus x0 to the alpha plus 2, x minus x0 to the alpha plus 3. So this is an infinite sum of powers, but these powers in general are not integers, and they do not start with power 0. So we assume that the solution is given by this infinite sum, C0 times x minus x0 to the alpha plus C1 times x minus x0 to the alpha plus 1 plus C2 times x minus x0 to the alpha plus 2, etc. The lowest power in the generalized power series is not always an integer, so this power alpha could be a number like square root of 2 or 3.5, or it could even be a complex number like 2i or 1 plus I square root of 2, etc. And then, however, no matter what power we start with, all the powers will be that power plus some positive integer. So if the first power is, for example, minus square root of 2, then the next power is minus square root of 2 plus 1. And then after that, minus square root of 2 plus 2, minus square root of 2 plus 3, and so on. So now part of the problem is that we have to find the lowest power alpha, together with the coefficients C0, C1, C2, etc. in the power series. So we have one more unknown, the smallest power alpha. And in general, there will be several possible values of alpha, and for each of these values, there will be a valid solution. Now, Frobenius' theory guarantees that if we find all the values of alpha, then for each alpha, there is a generalized power series solution. And these solutions together span all the solutions to the equation. So all solutions to the equation are a linear combination of these solutions, one solution corresponding to each alpha. There is an extra possible complication. If the difference between two of these alpha values is an integer, then this is a special situation called the resonant case. Then some of the solutions to the equation can contain logarithms instead of, or actually on top of, a generalized power series. So it will be some logarithm times a generalized power series. And we will try to avoid this case in our course. It's just an extra complication in the computation, but let us deal with a case without logarithms. So now the next step is we want to find out the power alpha that starts the generalized power series. So let's look at an example and see how this is done. Consider the equation x squared y double prime plus 2xy prime plus x cubed plus x plus 1 times y is equal to 0. And let's try to solve it around the starting point x equals 0. So if x equals 0 were a regular point, then we could solve this equation by power series. We wouldn't need generalized power series. So let's see whether that's the case. First, we bring the equation into the standard form y double prime plus 2 over x y prime plus x cubed plus x plus 1 over x squared times y is equal to 0. So we divided by x squared, and then we got y double prime by itself. So now the coefficient of y prime is 2 over x, and the coefficient of y is x cubed plus x plus 1 over x squared. Unfortunately, these functions are not continuous at 0, therefore they cannot be analytic. So this means that 0 is not an ordinary point, and we cannot solve this equation by power series for an initial condition starting at x equals 0. Okay, so now let's check what kind of singular point 0 is. So since x times p is equal to 2, and x squared times q is x cubed plus x plus 1, well, both of these are analytic functions, both of them are polynomials. So this means that x0 is a regular singular point, and we can use Frobenius method to solve the equation for some initial condition at 0. So now let's finally use some generalized power series. Let's write the equation again in its initial form: x squared y double prime plus 2xy prime plus x cubed plus x plus 1 y is equal to 0. And since we know we can use the Frobenius method, let's set y of x equal to some generalized power series. So in our case, the starting point is 0, so then the generalized power series can be written as C0 x to the alpha plus C1 x to the alpha plus 1 plus C2 x to the alpha plus 2 plus C3 x to the alpha plus 3, and so on. So we use this expression for y to write all the 5 terms in the equation as generalized power series. So in the equation, we have 5 terms: x squared y double prime, 2xy prime, And then I split the expression involving y into three terms, namely x cubed y, xy, and y. So first, we take the derivative of y in order to get y prime, and we take another derivative to get y double prime. So now we take the derivative term by term. First one is the derivative of c0 x to the alpha, and we get c0 alpha x to the alpha minus 1. Then the derivative of c1 x to the alpha plus 1 is c1 times alpha plus 1 times x to the alpha, etc. And we take one more derivative to get y double prime. So the derivative of c0 alpha x to the alpha minus 1 is c0 times alpha minus 1 times x to the alpha minus 2, etc. So notice that unlike for the usual power series, now when I take the derivative, none of the terms necessarily becomes 0. So for the usual power series, if we have c1x, the derivative of c1x is c1, and then if we take another derivative, the derivative of c1 is 0. Here, no matter how many derivatives we take, it is not guaranteed that any of the terms will become 0. They just remain there, and the power always decreases by 1. This is because alpha is not usually an integer. So, for example, when you take the derivative of square root of x, no matter how many derivatives you take, you wouldn't necessarily get 0. While on the other hand, if you start with an integer power like x squared, if you take 3 derivatives, you get 0. The derivative of x squared is 2x, the derivative of 2x is 2, and the derivative of 2 is 0. So here that doesn't happen. No matter how many derivatives you take for generalized power series, in general, all the terms will still be there. So now using these derivatives, let's actually compute the generalized power series of the terms in the equation. So x squared y double prime, we take the power series of y double prime and multiply all the terms with x squared. So in the power series of y double prime, the first power is x to the alpha minus 2, but if we multiply it by x squared, we get x to the alpha. Then the next power is x to the alpha minus 1. We multiply it by x squared, and we get x to the alpha plus 1, etc. So this is what we have here. The first power is x to the alpha, the next one is x to the alpha plus 1, then x to the alpha plus 2, and so on. And because we just multiplied by x squared, then this does not affect the coefficients. So the first coefficient is 2c0 alpha times alpha minus 1. Then the next one is c1 alpha plus 1 alpha, then c2 times alpha plus 2 times alpha plus 1, etc. Now let's look at the power series of 2xy prime. So we get this by taking the power series of y prime and multiplying it by 2x. So in the power series of y prime, the first power was x to the alpha minus 1, then next one is x to the alpha, then x to the alpha plus 1, etc. So if we multiply this by x, Then the first power will be x to the alpha instead of x to the alpha minus 1. Then the next power, when we multiply x to the alpha plus 1 by, when we multiply x to the alpha by x, we get x to the alpha plus 1. And when we take x to the alpha plus 1 and multiply it by x, we get x to the alpha plus 2, etc. And since we multiplied by 2x, not by x, all the coefficients are also multiplied by 2. So I get 2c0 alpha x to the alpha plus 2c1 alpha plus 1 x to the alpha plus 1, etc. What about the other two terms? So the power series of x cubed y is, we take the power series of y and multiply every power by x cubed. So instead of x to the alpha, we'll have x to the alpha plus 3. Instead of x to the alpha plus 1, we'll have x to the alpha plus 4, and so on. And xy, almost the same thing. So we take the power series of y, which is actually written here, and we multiply every power of x by another x. So instead of x to the alpha, we'll have x to the alpha plus 1. Instead of x to the alpha plus 1, we'll have x to the alpha plus 2, and so on. All right, so this gives us the power series of xy. And finally, there's also a term of y in the equation. So that's given by the original generalized power series. So now the sum of these 5 expressions for x squared y double prime, 2xy prime, x cubed y, xy, and y is 0. So again, just like for a power series, this means that the coefficient of every power on the left-hand side is equal to the coefficient of the same power on the right-hand side. But on the right-hand side, we have 0. So this means that the coefficient of every power on the left-hand side is 0. So in order to compute the coefficient of each power on the left-hand side, we collect all the terms containing that power and set the sum of their coefficients, that is the total coefficient for that power, to be 0. So now there are 2 cases. Doing this for the lowest power present in the equation, so the lowest power in the generalized power series, will lead for an equation to an equation for alpha itself. So this is how we find what alpha has to be. We set up the equation for the lowest power present in the original equation. We compute the coefficient corresponding to the lowest power in the equation. And setting it equal to 0, we get something called the initial equation. So this is the equation that comes from the coefficients for the lowest power, and this enables us to compute alpha. So the lowest power in the equation plays a special part. Solving the equation for that lowest power enables us to compute alpha. And on the other hand, doing this for higher powers present in the equation will enable us to compute the other coefficients in the generalized power series, namely C1, C2, C3, etc., as opposed to the first equation from which we will compute the power alpha. So the first one plays a special part. In this course, we'll only look at the first one, at the initial equation. And next time, we'll compute some coefficients as well. So notice that we actually do not need to compute the first coefficient, C0, because the equation is linear. We actually have the freedom to set C0 to be 1. That is, because the equation is linear, we can multiply a solution of the equation by a constant, and we still get a solution. So if C0 is any non-zero number, then we can multiply the whole generalized power series by 1 over C0, and then we get a solution in which C0 is 1. And C0 equal to 0 is impossible by definition, because C0 is the coefficient of the lowest power in the generalized power series, so it cannot be 0. If it were 0, then the lowest power in the generalized power series would actually not be present in the generalized power series. So we would be starting with some other power, and that power would be the lowest power, not this one whose coefficient is 0. So C0, by definition, cannot be 0. Let's compute the coefficient of the lowest power in the equation, which, as I promised, will give us the initial equation. The lowest power present in the equation is x to the alpha. So of all the terms present in the equation, there are 3 places where x to the alpha appears. There's this C0 alpha times alpha minus 1 x to the alpha that comes from x squared y double prime. There's 2C0 alpha x to the alpha. It comes from 2xy prime. The next term does not contain x to the alpha, so x cubed y does not have any term with power x to the alpha. The next term, x times y, also does not contain x to the alpha. It starts with power x to the alpha plus 1. And finally, the last place from which we get x to the alpha is C0 times x to the alpha from the power series of y itself. And again, notice that y is a term in the equation. It comes from multiplying the parentheses x cubed plus x plus 1 times y. So 1 times y gives a term of y. So we had x to the alpha in 3 places, and we had C0 alpha alpha minus 1 x to the alpha, 2C0 alpha x to the alpha, and C0 x to the alpha. So on the left-hand side of the equation, this generalized power series has x to the alpha with the coefficient, the sum of these 3 coefficients, it's C0 alpha times alpha minus 1 plus 2C0 alpha plus C0. So C0 alpha alpha minus 1 plus 2C0 alpha plus C0. And since everything on the right-hand side is 0, this means that the coefficient of alpha of x to the alpha here must be 0. So C0 alpha times alpha minus 1 plus 2C0 alpha plus C0 must be 0. Now, since, as I mentioned before, by definition, C0 is non-zero, we can divide the equation by it, and we get the initial equation, alpha times alpha minus 1 plus 2 alpha plus 1 is equal to 0. So this is the initial equation. It's the equation that we get by looking at the coefficient of the lowest power that's present in the equation, and then dividing this equation by C0 because C0 is a non-zero number. So this is an equation that involves alpha only. So let's write it again. Alpha times alpha minus 1 plus 2 alpha plus 1 is equal to 0. This is a quadratic equation. So this is alpha squared plus alpha plus 1 is equal to 0. And solving this quadratic equation, we get two values of alpha by the quadratic formula. Alpha is minus 1 plus or minus square root of minus 3 over 2. And square root of minus 3 is equal to square root of minus 1 times square root of 3. So since square root of minus 1 is I, we get the two solutions, minus 1 plus I square root of 3 over 2, and minus 1 minus I square root of 3 over 2. So these are complex roots. So our generalized power series, when I solve this equation, will have complex powers. So one more thing to check. Are we in the resonant case, and will we need to use logarithms in addition to generalized power series? To find out, we need to compute the difference of the two roots. So alpha 1 minus alpha 2, it turns out to be I square root of 3. Since this is not an integer, we are not in the resonant case. So our solution will only involve powers of x, but it will be complex powers of x. So the next step, which we will do next time, either for this equation or for a similar equation, is that we'll compute one solution for each solution of the initial equation. So for each of those two values of alpha, there will be a solution. For each of these solutions, we can take, with no loss of generality, the first coefficient to be 1. So C0, I took C0 to be 1. And after we find these two solutions, every solution of the equation can be expressed as a linear combination of these two solutions. So every solution of the equation is equal to some constant times the first solution plus some other constant times the second solution. We'll compute these two solutions next time, by which I mean we'll compute some of the coefficients in the generalized power series, C1, C2, C3, etc.